There we go. Before we start, I want to remind everyone of our community statement and our agreement that we are all learning, everyone has something to contribute, and no one has all the answers, not even the speaker. If you have questions during the talk, feel free to put them in the chat. Portia, the organizers will monitor the chat so you don't have to, and will interrupt you if there's a question, or people can respond in the chat throughout. And then today our speaker is Portia Anderson, and she's speaking about geometric manifestations of an inequality of Littlewood-Richardson numbers seen through comparing skew tableau counting rules.
Well, thank you,
Thanks,
Prairie.
Portia.
Thank you to Prairie for inviting me and waiting so long for me to respond and send my abstract and title, and for helping me know what I was going to talk about. Okay, also, be honest, I had not practiced this. Like, I just finished my slides. We'll see how we go. Okay, so this talk is going to be about something that's really plaguing me and has been for a long time. And then I'm going to ask at the end if anybody knows the answer and if they can tell me. Okay. Okay, here's one of my slides. Okay, combinatorics. I love the combinatorics community. I don't really know any combinatorics. I don't identify as a combinatorialist, but I love being part of your world. So I have like one open question, which is like, what is the ranking of funness of mathematical communities? We know number one, but does anybody have a spot 2 suggestion or spot 6? No? What's the least fun one? Maybe that shouldn't be recorded. Okay, well, we can debate that after. Okay, whoa. Okay, I don't know why this is so pixelated, but yeah, okay, here's just this constellation, this cloud of things that are going to show up. This is the slide that I wasn't finished making. So okay, so then this is gonna, you can see my mouse, right? I guess so. This is going to be the equality of Littlewood-Richardson numbers that we're going to be talking about. And it's going to be connected to a bunch of different things, including these. And they're all going to be spiraling around this equality. And basically, the moral of the story was that I was plagued by, I guess these are kind of almost, well, okay, I was plagued by this one and this one. This is like in Schubert calculus, intersection theory, cohomology stuff. And this is also kind of that. And then I was trying to figure out those versions of this same thing, and also with puzzles. I do stuff with puzzles too. And then I did not know the answer, and it was very hard and complicated. Then one day I just made this trivial observation which implied this, and then it implied all these things. So that's what I'm talking about. And then we're going to go back to the other direction at the end, which will be the open question part, I guess. Okay, first, probably most combinatorics people are familiar with partitions, but I'm going to say anyway that everything here is going to be indexed by partitions. And a partition is just a way to split up like an integer n into a sum of things that add up to n. And we're going to represent partitions as Young diagrams, which is you just take your n boxes and just stack them so they're aligned at the top and to the left. And this is just an example that shows like how you can correspond the Young diagram to the most usual way of expressing a partition. So yeah, we have 6 boxes, then 4 boxes, then 4 boxes, then 2 boxes. So that is the Young diagram for that partition. And yeah, so these lowercase Greek letters are going to be showing up all over the place and in every context, basically, you can just think of it as a partition. Okay, now, what are Littlewood-Richardson numbers? They're very important, I gather. So here are a few things. The Littlewood-Richardson numbers are structure constants of the ring of symmetric functions for the basis comprised of Schur functions. So the structure constants are the coefficients that appear when you expand a product of two Schur functions as a linear combination of other Schur functions. So these are the Littlewood-Richardson numbers are appearing in there. And then they are also the structure constants of the cohomology ring of the Grassmannian for the Schubert variety basis. So it pretty much just looks the same. And it kind of is in a way. So, and then that's kind of the world I normally do things in, is I do Schubert calculus stuff and geometry stuff mostly. And yeah, a lot of other things probably. Okay. So, is this really like pixelated to you? I guess it is. Oops. I don't know why that is, but anyways. So there's a bunch of combinatorial interpretations of Littlewood-Richardson numbers. And this list is just screenshotted from what is a combinatorial interpretation by Igor Pak. So you can just find that if you want this. It's like a pretty nice list. So there's a lot of different ways to do it. Oh, okay, yeah. Okay, and I just want to draw attention to something right here, which is the bottom of this thing. Okay, first of all, this is my idol, Kevin Purbu. I don't know what to say. Like, I read one paper of his, which is this paper about mosaics, and I really loved it. And he's also my brother. And then over the summer at the Schubert conference, I accosted him in a Mediterranean place and told him he was my idol. And he said that was weird. And I loved it. I think he did too. And also, my BFF Paul is down here too. Paul Paul Jean Justin, or is that how you say it? Or is it Zin Justin? I don't know, but he's down here. And then puzzles, here's the other notable one. I do a lot of puzzle stuff, and the other day, like 2 days ago, I realized that when you Google Knudsen Tau puzzle, a video of me talking about puzzles is the first result. That really, I thought that was really hilarious. And terrifying. Yeah. If Paul is watching this, then you know how awkward that is, because well, both that you're watching it and because of this thing, because we have a shared phobia of recordings of ourselves. Okay. Now, oh, and then yes, the other thing I'm going to focus on here is like the geometric interpretation of these numbers, of course. And so I'm just going to give a little bit of info on that. And then this is like what Schubert calculus is kind of about. So, which is like kind of computing the Littlewood-Richardson numbers in a geometric way, or in terms of like the cohomology ring of the Grassmannian. Okay, so Schubert varieties are certain projective algebraic varieties that live inside the Grassmannian of k-planes in Cn, which is like k-dimensional subspaces of n-dimensional complex space. And so that itself is a projective variety. And then the Schubert varieties are indexed by partitions that fit in a k by n minus k rectangle. So it corresponds to like the numbers k and n, for like how big the planes are and the size of the ambient space. And the Schubert varieties, as I think I mentioned a little bit earlier, give a basis for the cohomology ring of the Grassmannian. And you just like, basically this is just the homology class defined by the Schubert variety. And then, you know, the Grassmannian has Poincare duality, so we can view it as a cohomology class. And then Schubert calculus is what we call the activity of finding these structure constants, or the Littlewood-Richardson numbers, or the Schubert variety basis. So this thing that I showed earlier, and the way we can solve that problem in terms of like geometry and intersection theory, I suppose, or enumerative geometry, is the following. So if you want to find C lambda mu nu, you can take the Schubert varieties indexed by lambda, mu, and nu, except this one is an opposite Schubert variety indexed by nu, and I'm not going to give any detail about that. But then, and then you perturb them, meaning like you move them so that they're in general position, so they're not like overlapping each other or in special position in any way, so that the intersection is transverse. And then you count the points in that intersection of 3 Schubert varieties. So like that intersection is right here inside the brackets, and the G is just from basically what happens, what we need to do to perturb. So don't pay too much attention to that. But anyways, like if the transverse intersection is finite, then this integral, which it counts the number of points in the intersection, and otherwise the integral equals 0. Is there anything else I wanted to say about that? Oh, the integral is push forward to a point. That's one of my life mottos. Okay, is that good? Oh, okay, wow. Okay, I need to proselytize about Schubert calculus first, because I think that you guys should all start moving over to Schubert calculus. Okay, so reasons why I love Schubert calculus is, number one, Schubert is an icon. And like, these are some of my good memories of Schubert. And this is part of my conspiracy board. And yeah, like, it is what it is. Okay, 2, Schubert calculus people love to juggle. And you can follow my Instagram, Schubert's Balls, for like our, you know, cross-institutional juggling troupe, which we began at the Schubert conference. DM for business inquiries, please. Okay. Any questions right now? All right. Okay. So Schubert calculus, I'd say, is maybe, or maybe it can be a party field, you know, like when you go to college and it's a party school, like I feel like Schubert calculus is the party field of math. The evidence, well, yeah, FIPSAC was wild. So I can't actually show that, but like let's make Schubert calculus the party field of math. I mean, it's like work hard, play harder kind of thing, because I do work hard, you know. Mark Denker says, thank you for not sharing the FIPSAC videos. Yeah, I know, right? Okay, somebody said something. I don't know what that says. Okay. Here's another reason. Schubert calculus connects a bunch of different areas of math. And this is actually like mathematically why I actually do like it. I mean, I had kind of an awakening of Schubert calculus over the summer because I had been doing it for like years, I guess. But then I had kind of like a born again moment. I mean, mostly it was the first 3 bullet points, but this one is also there. So like, I like Schubert calculus because it connects a bunch of different areas like geometry and combinatorics, or I'm pretty sure representation theory is like definitely in there, but I'm not really sure because I never understand representation theory. But a lot of my work has to do with like just shifting perspectives and going back and forth between like looking at something from the combinatorics end and then saying, oh wait, that would imply that this thing, like the geometric version or manifestation should be true over here, and I didn't know that or expect that. And then you say, well, why is that true for geometric reasons, and like vice versa. So and you can kind of understand a phenomenon more, like the more you just jump around looking at it in all the different like various ways. So that's very interesting to me and something I enjoy doing. And so I guess this is, yeah, kind of just saying that. And this is kind of the theme of this talk and previous talks and research I've given about like edge swapping of Knudsen Tau puzzles. But yeah, so this talk is going to be like, I was trying to prove something difficult geometrically, then I found this very easy combinatorial thing which proved everything, but now I want to find the geometric proof and then maybe prove the other direction. Okay. Oh, and if you like geometry, Schubert calculus is for you. If you like combinatorics, Schubert calculus is for you. That's for sure. If you like representation theory, Schubert calculus is for you, probably. Because I can't speak for them because I don't know representation theory. But if you like PDEs, Schubert calculus is for you. Schubert calculus is for everyone. So guys, please, like if I do get a job, I'll be here waiting for you to come to Schubert calculus. You can take up a new interest, right? Okay. Okay, this is like, yeah, one of my hasty slides. So the plan going forward after that interlude, we're going to go back to what we were doing, which was looking at Littlewood-Richardson rules. And we're going to look at 2 specific ones that involve counting skew tableau. And then we'll use that to make a connection to a geometry / Schubert calculus statement. Okay, now we're going to define tableau. And okay, so probably people the chat is funny. Thank you guys for responding. Okay, so a tableau, a semi-standard Young tableau, or we'll just call them tableau from now on, is a way to fill a Young diagram with positive integers such that they are weakly increasing across each row and then strictly increasing down each column. And so this is just an example of what that looks like. Here's a tableau on the partition, or the Young diagram over here. And probably people have dealt with these before. Okay, and now skew tableau are like a very similar thing, but it's just now we've cut out a piece of the Young diagram and then we're labeling the remaining part. So to put it more precisely, if you have 2 Young diagrams for partitions nu and lambda, such that lambda is contained in nu, so here the outer one, the entire outer thing would be nu, and in here would be lambda. Okay, the skew diagram is denoted nu mod lambda, right? And that's what you get when you remove lambda, and we show the remove part as shaded. Okay, and then a skew tableau on that shape is just filling it with integers that satisfy the same conditions as with the regular tableau. So weakly increasing across each row and strictly increasing down columns. Okay, so then there's just an example. And then the next thing we need to talk about this, these rules, these Littlewood-Richardson rules, is this operation called rectification, which I'm not gonna like go super into talking about what the method is, but it's like pretty simple. It's in Fulton-Young Tableau, like everything else I know. Okay, so then basically it's just taking a skew tableau and moving around, shifting the boxes so that eventually you get rid of the empty hole that was there. And I'll just say what it is. I mean, they call them outer corners, I believe, but like a thing that's sticking out with a corner here, and then you move the smallest of the boxes to the bottom or right into that empty space. And if the numbers are equal, then you move the bottom one up, and then you basically just like keep filling in the holes until you get to a tableau. Okay, so then now we're gonna get into these rules for counting these skew tableau that'll give us the Littlewood-Richardson numbers. Okay, so let's say we're going to use these examples of like, let's have these be our lambda, mu, and nu Young diagrams for the sake of visualization. Okay, so let's take any given tableau U on the shape mu, and we define this set, which this this like math cal S set nu mod lambda comma U circle. So this is just the set of skew tableau on the shape nu mod lambda that rectify to this given fixed tableau U naught on mu. So this is just shown here in a much more easy to visualize way. So yeah, you take your nu and you cut out your lambda to get this, and you have skew tableau on this remaining bit, and then anything that is a skew tableau there that rectifies to a certain fixed tableau over here is in this set. Okay. Hooray. Okay, then we have a second set that we define. This is like a math cal T set. And for this one, it's also, well, these two sets are going to end up having the same cardinality. But so this one is denoted math cal T, lambda star mu comma v naught. And so this lambda star mu notation means the skew diagram you get if you like join lambda and mu together so that the northeast corner of lambda is touching the southwest corner of mu, like so. So just means that you like take lambda and mu and position them like this to make a skew diagram. Okay, and then yeah, this set is just all the skew tableau on this shape, lambda star mu, that rectify to a certain fixed tableau v naught on nu. Okay. And okay, so those were the definitions, and then these are the rules. The Littlewood-Richardson numbers are just given by the cardinality of those sets. So they have the same cardinality, and they both equal c lambda mu nu. Okay, and this is just to summarize both of those cases for like this particular example, just see what it looks like, just to remind us. So yeah, these sets have equal cardinality. They both equal c lambda mu nu, the cardinality does. And then, so what we're going to do now, though, is we're going to look at this case and see, well, we can kind of formulate the situation in terms of rule 1, except now like our new in this case is going to be this entire thing, and then the lambda that we remove from it is going to be like this black section here, and then our new Greek letter nu is going to be what was nu. I mean, that's so confusing. I'm just going to say this is what it's going to be. So we're going to take a different triple, which is, and then apply rule 1 to that. Okay, so this is what I was trying to talk about. So now let's define a new, I keep saying new, but it's like the Greek, a new triple of lambda, mu, nu, and I've denoted them with tildes so that we distinguish them from the others. Okay, so now we have our new lambda is this box, like I said, so we're going to remove that from this new shape, which is made of, it's like what was lambda star nu, except it's not skew, but like the piece that was removed is there now. And for some reason that I'm not going to try to explain, I'm calling this mu lambda. This entire shape, this diagram is going to be denoted mu lambda, and that has other reasons to do with things that I will not detail here. So just tolerate that. Okay, and then, okay, let's apply what was rule 2 to this, where we're like taking this overall thing and then removing this guy and then rectifying to this. And then we see that that was exactly just the same set as appeared on the previous slide right here. So we have like this T, A, out. Oh my God. Okay, this is supposed to be say lambda and mu, not alpha and beta. Sorry about that. Okay, it's correct over here though. So anyways, those are the same. And then we just get this equality. And so that like corresponds to two different Littlewood-Richardson numbers. And so that gives us this equality of Littlewood-Richardson numbers, which is like the main equality that this talk is going to be about. So, okay.
A quick question.
Yeah.
That row that shows up here, that's always going to be a rectangle, right? Because it comes from putting those things corner to corner.
Yes, yeah, exactly. So it's always going to be a rectangle. Yeah. So I could say more, but I won't. I'll keep going. And then we can talk about it or anything else later. Okay. Right. So this equality is very trivial to understand from this perspective. But I had never thought of that, and I didn't know about it, and I never had any reason to like in my own work to ever think about it. And then so it turned out that this like trivial thing was something that I discovered after a long struggle with geometry things. Okay, so there's going to be a slight little story time about that journey right now. So originally, okay, so this equality right here of Littlewood-Richardson numbers, the like translation of that into intersection theoretic Schubert calculus formulation is this, like you can write it as this equality of integrals, which are, these are like counting intersection points of these triple intersections of these Schubert varieties. And so basically I arrived at a point where I wanted to understand this, and I was completely ignorant of the fact that this equality was true by skew, tableau, partition reasons. Okay, so then why did I care about this equality in its geometric incarnation? Well, I wanted to understand some coefficients, which I'll call d lambda mu nu, that arise when you expand the images of some basis elements of the homology of the product of Grassmannians under the direct sum map to a larger Grassmannian, and you want to know how you can write that as a linear combination of basis elements of the homology over here. So like that is probably not something that anybody understood me when I said that just now, or that they want to, like, I don't know. But you can if you want, but it would take more doing. But so that probably means nothing. So that's okay though. Anyways, so basically, yeah, I have this map, this direct sum map where you take like a product of Grassmannians, and then you, for a plane, you know, well, this time it's an L1 plane and an M1 plane, but you take the planes from each Grassmannian and then you direct sum them, and then that gives you an element of the larger Grassmannian. And then basically where I'm in other things in math or my own work, I needed to think about like the push forward map, like on homology induced by this thing. And I needed to like think about how to expand out the image of a basis element in as a linear combination of Schubert basis elements, basically. So these things are those coefficients, and they have plagued me. And they actually come up. They are central in a way to my project, which this kind of branch like sprung out of that, which is like about edge swapping symmetries of Knudsen Tau puzzles with different shape boundaries. Like usually a puzzle is a triangle, but I was doing it with parallelograms or trapezoids or hexagons, and saying like you can swap, you can commute edge labels, and it preserves the constant that it computes. But the proof of that kept involving these coefficients. And then even more than that, I was trying to extend things to like K-theory versions and whatnot. And then I understood those coefficients even less. So I like wanted to understand them. Okay. So those coefficients plagued me basically. Oops. And the other thing was that the only reason I could do anything was that I had heard vaguely that they are just the Littlewood-Richardson numbers, actually. And then there's a paper by Alan Knudsen and Matthias Lederer that quotes this in the very beginning, or says it, but like there's no explanation. It's maybe just like known. And you know, my advisor had said there was maybe some ugly proof about Pierre rule, which I don't understand that. And then he didn't know, he wasn't aware of like this way that I'm talking about of showing that I'm going to say that you can show this. Well, this partition thing basically. So it was very ugly basically, and there's no geometric explanation as far as I could tell. And that really was annoying and frustrating to me, because it seemed like it should just be able to be kind of, it seemed like maybe it could be very simple to just prove it cohomologically. And I kept trying to do that and failing. And then, yeah, when the K-theory problem came along, I really felt like I needed to understand them like once and for all. And then I started trying very hard. Okay, so then now I proceed with this story. Now we're right here in the story. So then, okay, one thing I did know was, for almost by definition, pretty simple geometry reasons, you could write this d lambda mu nu thing as this Littlewood-Richardson number, which is on the other side, and like it equals this integral. Okay, for intersection theory geometry reasons that I won't explain. And then, so I was trying to like make a geometric connection as to like why this thing should equal this. And then in doing so, I would have proved that like this coefficient is the Littlewood-Richardson number it is supposedly be. And so I was trying to like prove this starred equality, and then therefore it would prove the outer things were equal. And I still have not done that, and it still bothers me, and I'm still trying to do that. But then along the way, I somehow landed on the observation of this partition skew tableau thing I just said that told us this. And then that just instantly proved the other direction. So it proved that these geometry things were equal. And then it proved basically this mysterious fact that like had plagued me so much, because like I didn't have any proof for it that I was accessible to me or known to me. And then now this gave me one, which was like very beautiful. And also my advisor didn't know about it. I don't know if anybody, I don't know who else in the world doesn't know about or does, but there it is. Okay. So that was fun. That was, well, yeah, that was pretty nice, I guess. Unless, I think it's not, I think it's right. I think I mean, please let me know if I am saying anything wrong, because like that's a possibility, but I don't think this is wrong. So this trivial observation on the partition skew tableau side, then, like I said, basically spits out a very immediate and simple, nice proof of all these other statements that happen in different settings. So here is that push forward coefficient geometry cohomology thing. This is this equality of integrals is talking about like, it's like an enumerative geometry thing where it says the number of intersection points of these three Schubert varieties should equal the number of intersection points of these three Schubert varieties. And like that means I don't know, like I guess I felt like there should be some way to see why that would be true, but I'm still looking for that. And then here's the puzzle version of it. Like, so puzzles are like this doesn't tell you much about them, but imagine these are filled with pieces, puzzle pieces, but puzzles are like you label the edges with strings of ones and zeros, and the ones and zeros correspond to a string corresponds to a partition, because like you can index like strings in a k by n minus k rectangle, or sorry, partitions that fit in k by n minus k rectangle are in bijection with binary strings with k ones and n minus k zeros, because you can just start at the bottom of the rectangle and then like step, like do a 1 when you step right and a 0 when you step up, and then you just go up. So that's how we like turn our partitions into strings, and then those are what label the puzzles. Okay, and then basically we compute like how many, we count the number of ways to fill puzzle boundaries with puzzle pieces that are labeled in a certain way. And this this equality says that these two sets should be equal, essentially. That probably is not very meaningful to anyone here, maybe, but I also don't know why this is true just on the combinatorics puzzle side of the spectrum, because in theory maybe you could prove that this is true directly by showing that the number of, like using actual puzzle pieces to show that the number of these sets, the cardinality of these sets is equal, but I have no idea, and I'm not very good at combinatorics or anything. So the other thing to note over here is that actually this can just be seen as a trapezoid puzzle, because like the thing about this is that it's a trivial piece and you can just cut off this triangle basically, because this labeling forces the inner edge to be labeled like this. So you can just like cut this thing off and have a lambda here, and then you have this trapezoid. So it's kind of like this Littlewood-Richardson number corresponds to trapezoid puzzles, and the trapezoid puzzles are kind of a fundamental building block for like my parallelogram and hexagon puzzle proofs. Also, Pasha Piliovsky asked me about trapezoids at one point, and so maybe I'll tell him about this one day. I don't know. He might be interested in it. Okay. So yeah, that is like the implications of this thing that we just observed. That's pretty notable to me. Like I was pretty shocked by that. And then, so the other direction still is a question, because like I still haven't understood these things geometrically, and I still want to. I mean, the fact that it's shown in the skew tableau rules feels like an even bigger motivation for me, because then I would have like if I were to figure this out geometrically, then it would be like a geometric proof of something about these skew tableau partition goings on. So, or just like a manifestation where we can say, well, this very fundamental like equality holds in the world of like counting skew tableau, and then here's the parallel manifestation of it in terms of geometric Schubert calculus with intersection theory of Schubert varieties, or like enumerative geometry. So if I wanted to still want to find the parallel geometric understanding that corresponds to that, which I think would be cool, and also I want to understand the geometry for K theory and other cohomology reasons and beyond. So these are the still open statements, like, can we prove any of these things in a more native way without already knowing that this is true because of the skew tableau business, and thereby prove something about the skew tableau by going in this direction first? And I realized that this is more complicated than I thought, because I thought that maybe I would like give a talk and then everybody would raise their hand and say, oh, I know what it is. Like, you just do this, but I don't think that's gonna happen actually. Because I don't know, does anybody know right now? Like, does anyone know? No? Okay, well, if you ever do find out, or like you want to find out, you know, hit me up, because I'll be here with this. And okay, so basically this is the end. This is a slide that I didn't finish writing, but it's an acknowledgement slide. All of you are kind of mentioned here. Aditya, yeah, you're here, and Mark. Okay, Mark's dancing. Yeah, okay. These are just basically inside jokes from combinatorics conferences, which are so great. Okay, that's it. Thank you.
All right, let's thank our speaker. There we go.
Any questions about
Questions for
this?
yeah,
Wow.
energy. I see one hand. Go for it.
So what exactly is mu lambda? How do you define it? I wasn't paying
Mu-
attention at that spot.
Wait, sorry, which one?
Mu lambda, the product, so to speak, of the two partitions.
Okay. Yeah, I'll go back to that. So this is what I'm calling mu lambda, this whole entire shape with like,
Oh, so you just connect them at the tip.
yeah, like it's as if we did this, except now this part is not removed, it's also filled in. So it's like we took this, you know, block, this thing called row, and then like each piece is just glued together to make a non-skew diagram. It's just a Young diagram made of these pieces.
Mm-hmm.
And Yeah, the reason why, if anybody is curious why I have denoted it mu lambda like this, is because of the reason I mentioned before, like you can correspond partitions to binary strings where like so in order to do that, well, in the way that I would is that you would start here and then read downwards as a string of like ones and zeros, and then that would tell you what partition this is. And then when you do that, like mu comes first in that order. So in my work, I just talk about like concatenating strings, and then that would concatenating those two strings, the string for mu and the string for lambda, would be what would give you this entire partition. So that's why it's called that.
So I have a question. Wait, can you hear me?
Yeah,
Okay, very nice talk.
thank you.
The equality, I'm looking at this equality and thinking about the various symmetries of the Littlewood-Richardson coefficients. So if you switch just lambda and mu here, the left-hand side shouldn't change, but something's happening on the right-hand side, right? The row gets conjugated, basically. What is that telling you?
So you're saying like if you were to switch lambda and mu,
Just
and then
switch the
what-
order, yes.
and then what it would look like over here. Yeah, so then it would look like you would have I guess you'd redo the whole thing, but now your blue mu would be here, and then your red lambda would be here, and then the like black cutout box or row would be like a different size box. It would be a 3 by 3 in that case.
Right. So
Yeah.
it looks like the right-hand side is changing while the left-hand side isn't.
Let's see. Yeah. What happens there? I don't think if that would like I'm actually like kind of confused. I mean, what would that do? Would it put it, I mean, I always think about things in terms of like Grossmanians and stuff, but I mean, basically, yeah, it would turn this into a different looking thing. And yeah, that would be the same number too. So I guess maybe that's what maybe you're asking, where like on this side it doesn't change anything, but if you the corresponding change over here makes this look like something different, which might not be super obviously the same.
Right, exactly.
Yeah. Yeah, that's true. I think when you get to the geometric like way to think about it, that seems kind of like trivial as well, but it's not really trivial to just see it like if you're thinking about the partitions. So yeah, I'm not well, maybe there's like something I can say over here about that. So like if we were to do that, basically you would just switch the positions of, if you're looking at puzzles, like you would switch the positions of mu and lambda. And okay, no, I don't have enough background information written in this talk to say anything enlightening about your question about the geometry. No, it's, I mean, okay, yeah, but you would switch those, and then it's like kind of easy to see geometrically why that would be the same, like if you go through the puzzle to the Schubert calculus. But
The puzzles don't have a row in them. Sorry, can't you look, I can't really.
oh, okay, yeah, the row is gonna be this string. So like,
Oh, I see.
because
Okay.
row is a box, a rectangle, so that like if you were trying to do like the corresponding string that goes with a box, like if you start up, like if you have an ambient box like this, and then you're starting over here, and then you go like a bunch of zeros, and then you hit your ones, and then you start going down for the edge of the box, then you do more zeros, and then that's like the box, and then you just do more ones. So that's like we have this sequence of some zeros and then some ones and then some zeros and then some ones. So that string is the one that
I
corresponds with
see.
the row. Yeah.
Thank you.
You're welcome.
Yeah, I was trying to look, I was trying to find if there's a proof of this symmetry of switching the two partitions. I was looking at Nick Lore's book, which has the proof, but I couldn't find it.
Wait, what book?
So Nick Lore's book has this proofs of the symmetries of Littlewood-Richardson coefficients. So if you like switch those two partitions, I think you still preserve symmetry, but I'm not sure why.
You switch like the partitions
Uh,
in the ordinary
yeah.
one?
What I was
The same
saying,
thing Sheila was asking.
Yeah.
I mean, should be true because
Yeah,
true function multiplication is commutative.
I was
Yeah,
looking
definitely.
for-
That's definitely true.
It's
That
just
you can
seeing it
switch
on the
those.
other side.
I
Yeah.
remember talking about it, but there is a direct proof.
A direct proof of switching these things, or like
Yeah.
lambda mu. Yeah.
Yeah, so like there is a proof where you switch these and you can see that why they should be the same. But I can't remember it right now.
Yeah, I mean, I know that Fulton does it, and Fulton Young Tableau, I think, like shows like that these sets are equal when you switch those. Yeah, but that's the commutativity of those is like definitely well known in all the different contexts.
I mean, the sets are not equal, they're in bijection.
Yeah.
And the bijections can get complicated, I think, particularly for commutativity.
Yeah, the left hand side is still well known. The right hand side I can't find a proof for.
Yeah, well, yeah, basically the commutativity of the right hand side, or like whatever happens to the right hand side when you switch lambda and mu on this side, actually is something that I guess I've proven in my work. Like it's kind of, so I've done it geometrically. I have like a geometric proof of what we're talking about, but I don't know about the like tableau way or whatever. Any other questions?
Prairie has disappeared for me, so I think I'll take over the wrapping this up portion.
Okay.
So, if we don't have any more questions, let's all thank Portia again.
Thank you. I miss you guys.